Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. In this exercise, we have a disk which sits under a sphere and parallel to the xy plane. The sphere is shown here in blue. If the disk extends upwards along the positive z-axis and downwards along the negative z-axis, a cylinder is created, shown here in red, that penetrates the sphere. The cylinder will intersect with the sphere at various points along the surface of the sphere. This creates a solid, shown here in purple. It's the volume of the solid that we're going to calculate. Let's now take a look at this structure in 3 dimensions. The purple area shown here is the xy plane. If I add a disk parallel to the xy plane and extend along the positive and negative z-axis, we see a cylinder is created. If I now add a sphere, a solid is created along the z-axis and inside the surface of the sphere. It's the volume of this solid that we're going to find. Due to the symmetry about the xy plane, we can look at this problem as finding the volume of the enclosed surface in the upper hemisphere of the sphere and above the xy plane where z is equal to 0. We can then multiply the result by 2 to give the total volume of the enclosed surface, which will include the volume below the xy plane. If we take the equation of the sphere, we have z squared equals 16 minus x squared minus y squared. The upper hemisphere of the sphere is given by z equals the positive square root of 16 minus x squared minus y squared. Let's take a look at this in 3 dimensions. So this is the complete sphere, so where z squared is equal to 16 minus x squared minus y squared. And then here we see the upper hemisphere of the sphere, so that's where z is equal to the positive square root of 16 minus x squared minus y squared. Our first step in calculating the enclosed volume is to determine the region of intersection between the disk and the xy plane, so where z equals 0, and then to convert this region to polar coordinates. To find this region, let's take a look at the disk in the xy plane. The equation of the disk is x squared plus y squared equals 4, and as you can see, it's a circle of radius 2 centered at the origin. To find the volume enclosed between the surface of the sphere and the disk when extended along the positive z-axis, we'll find the area of the disk and multiply by a height component to find the enclosed volume. We'll then multiply this by 2 to give us the volume below the xy plane and therefore the total volume. Let's begin by converting the equation of the disk region from Cartesian coordinates to polar coordinates. To do this, we need to replace x with r cos theta and y with r sin theta. Making this substitution and factoring out r squared, we have r squared into the bracket of cos squared theta plus sin squared theta is equal to 4. And using the trig identity where cos squared theta plus sin squared theta equals 1, we're left with r squared is equal to 4. And taking the positive square root of both sides of this equation, we have r is equal to 2. Now let's look at what we need to do to find the volume. The volume is a double integral over the region capital R. This will sum infinitesimally small pieces of area, shown here as dA. When we multiply the infinitesimally small pieces of area by a height function, shown here as f of xy, this will give infinitesimally small pieces of volume. Now let's look at what happens when we sum or integrate from the origin of the circle to its perimeter, so in the r direction. When we integrate in the r direction, this will represent the inner of the 2 integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each area is the length multiplied by the width. So in this case, dr is the height and r d theta the width. So dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. When we sum or integrate in the r direction, for this exercise, we begin at the origin of the circle, so where r is equal to 0, and we travel to the perimeter of the circle, so where r is equal to 2, as we saw when we converted the region of intersection to polar coordinates. If we multiply an infinitesimally small piece of area, dA, by a height function, we get an infinitesimally small piece of volume, dV. So that's the height function, f of xy, multiplied by r dr d theta, which, as we saw, is an infinitesimally small piece of area. We can now define the limits of integration of the inner integral. The lower limit is the origin of the circle, so where r is equal to 0, and the upper limit is where r meets the circle, so where r is equal to 2. I'll deal with the height function f of xy shortly, but let's first find the limits of the outer integral, so that's where r rotates about the angles of theta. To do this, let's first visualize the scenario as r rotates about theta across the region R. As r rotates, it begins at theta equals 0 and advances 360 degrees or 2 pi radians around the circle. Each sector represents an angle of d theta. By summing each of the infinitesimally small sectors, we get our total volume as we multiply the area by a height function. We do this by integrating beginning at theta equals 0 and ending at 2 pi radians. Now we understand the region as we rotate about theta, we can define the limits of integration of the outer integral. The lower limit starts at theta equals 0, and the upper limit is where theta equals 2 pi radians. Now let's deal with the height component, f of xy. We have two functions representing the sphere and the xy plane, between which we are calculating volume. We need to subtract one function from the other to determine the height component. To facilitate this, we need to assess which of the two is larger when x and y are 0. So which is the top function and which is the bottom function? And in this case, it should be fairly intuitive. Looking at the equation of the upper hemisphere of the sphere, we have z is equal to the square root of 16 minus x squared minus y squared. And setting x and y to be 0 gives z is equal to the square root of 16, which equals 4. The equation of the xy plane is z equals 0. So in this case, our top function is z equals the square root of 16 minus x squared minus y squared. And subtracting the bottom function from the top function gives us our height component f of xy, which is equal to the square root of 16 minus x squared minus y squared. And now we need to convert the height component f of xy to polar coordinates. To do this, we'll replace x with r cos theta and y with r sine theta. After we make this substitution, we get the square root of 16 minus r squared into the bracket of cos squared theta plus sine squared theta. And using the trig identity where cos squared theta plus sine squared theta is equal to 1, we have a height function of the square root of 16 minus r squared. Now that we have our height component, we can begin to evaluate the integrals. Starting with the inner integral, we want to integrate from r equals 0 to r equals 2, the square root of 16 minus r squared r dr. To integrate this, we need to make a substitution. So first, let u equal 16 minus r squared. Du by dr is equal to minus 2r, and minus 1/2 du is equal to r dr. So now making the substitution for 16 minus r squared and r dr, we have minus a half multiplied by the integral of u to the power of a half du. And using the power rule to evaluate this gives minus a half multiplied by 2/3 multiplied by u to the power of 3 over 2. And now if we substitute back in for u, we're left with minus a third multiplied by the square root of 16 minus r squared all cubed, and we need to evaluate this between 0 and 2. So plugging in the value for r equals 2, we get minus 8 multiplied by the square root of 3, and that'll be minus 1/3 of the square root of 16 cubed when we plug in the value for r equals 0. And this all equates to 64 divided by 3 minus 8 multiplied by the square root of 3. And now working on the outer integral, we need to integrate from theta equals 0 to theta equals 2 pi, 64 divided by 3 minus 8 multiplied by the square root of 3 d theta, and not forgetting to multiply this result by 2 to include the volume below the xy plane. Using the power rule to evaluate this integral gives 2 into the bracket of 64 divided by 3 minus 8 multiplied by the square root of 3, all multiplied by theta, and this needs to be evaluated between 0 and 2 pi. And substituting 2 pi in for theta gives 4 pi multiplied into the bracket of 64 divided by 3 minus 8 multiplied by the square root of 3. And plugging 0 in for theta gives 0. And this gives us a final answer of 4 pi multiplied into the bracket of 64 divided by 3 minus 8 multiplied by the square root of 3.